Okay, thank you very much, Ellen, for the invitation and for the kind introduction. Indeed, when you read the title, you think of what exactly is he going to talk about? So I thought maybe I have to apologize for the somewhat grand title. It was inspired by your TACO SFB, because when Stefan asked me to send the abstract, I browsed through the SFB webpage and said, oh wow, cool! This is really the things that we actually would like to do, but perhaps we're not quite doing yet. So perhaps the bit more mundane and real thing that tells you what I'm actually going to talk about would be a title like this. So it will be mainly atomic force microscopy studies and a little bit of Confocal Raman in the very end. And we'll mainly do spectroscopy of mineral surfaces and photocatalytically. So strontium titanated, bismuth vanadate, to be very precise. That's sort of what I'm largely going to talk about. But as a motivation to make things even worse, let's say in terms of grand title, I do feel the motivation from the since I started to give a lecture on climate physics for the first time earlier this academic year. Where obviously, as you all know, well, our vast universe is not very friendly to life, and it's only this very super thin shell of 10 kilometers or so where that is our life support system. And of course, there are those two curves. There are two curves. The first one that you all know about the increase in CO2 concentration in our atmosphere. That tells us that we really need to do something about the way how we generate our energy or how we make it available to us. The second one that I also learned only in the course of preparing this lecture is this one, which is a simulation that shows what's going to happen when we stop at some moment and become CO2 neutral. And how the CO2 concentration relaxes in the atmosphere. And then you see, I mean, we're almost here, right? 425-ish or so is where we currently are. So if we stop tomorrow in the year 3000, we will still have the CO2 level on the Earth that is way above pre-industrial levels, which is this dashed line here at the bottom. And I mean, essentially, there's an enormous lifetime of CO2 in the atmosphere. And this year is still, in the very long term of thousands of years, incompatible with ice caps on the poles. Right? So that is something that we should be aware of. So there is we need to change our energy sourcing, and B, also the CO2 that we have already emitted. We should do something about it to bring it back down for future generations. And of course, for the first part, we think that in principle, there should be a solution. We should all know it. There is about 10,000 times as much solar energy coming on the planet as we're currently need as energy. So if we harvest that and turn it into well, either use it directly or split water to generate hydrogen or some other chemical source, then that should be enough. But the reality, of course, is somewhat dim, as you undoubtedly all know. Well, I'm carrying a bit else to Athens, I admit. But okay, I found these numbers that I looked up at the time quite impressive. So if you look at the actual amount of electric hydrogen that's produced from electricity, it's not this yellow part. It's the width of this black line here at the top well, this is from 2022, those numbers. But what we expect to have, according to the IPCC, what we should get in order to fulfill our 2-degree goal would be 100 megatons. So that's sort of the total production of mankind by 2030 in order to become CO2 neutral by 2050. So there is a slight challenge up to us. And I mean, basically, the vast majority we produce from fossil fuels at the moment of methane. So that's the disaster. And of course, many of you work on electrolysis and are fully aware of all the challenges that are around about the stability of the catalysts and the possibility to make that available. So I think what we'll need to do is really explore also various other alternatives, and one that we have sort of come in contact with, and that I will also talk about, is the question of, okay, is photocatalysis something that can contribute something useful to water splitting? And so Kazanougi Domen has this wonderful 100 square meter of solar panels in Japan installed that actually produce hydrogen and oxygen bubbles that come directly out of it. And so I'll speak a little bit about, that will be sort of the first topic that I'm going to work to, is the characterization of these photocatalytic materials for water splitting. Yeah, and then the second challenge obviously is to bring down that CO2 level that's already around, and that also there I think the question is even more challenging, because we have really not a clue what we should do. Of course, probably I can imagine that things like biological tricks, afforestation, soil fertilization to stimulate biology to do the job is probably the most useful approach. But of course, the other one is direct air capture that many people are working on, which is super inefficient. And even if you generate a whole lot, then the question is, what do you do with all this CO2? CO2 reduction, or do we need to pump it into these empty oil reservoirs? Or do we convert it into something else? And that is sort of the second part that I want to talk about, that we have started in recent years, and we're only sort of do our first steps. This is olivine. This is a mineral that contains a lot of magnesium that can be converted into magnesium carbonate, and that is then you have it back in the rock, in your CO2. And we'll try to understand a little bit how that works. But the challenge, of course, is what we need to sequester is gigatons per year after 2050 or so. So these are the big challenges. And okay, as AFM spectroscopists for solid liquid interfaces, so we can do a little bit on trying to understand this, and we can do our contribution to trying to characterize the solid liquid interfaces where all those reactions take place at the catalyst materials. Okay, so after that grand picture, a bit more mundane, what am I actually going to talk about? So I'll introduce to you, well, the methodology that we're using, that we've been developing over the years with AFM spectroscopy to characterize these interfaces and to learn the double layer. And then we'll apply that to various materials, in particular strontium titanate. We'll speak a bit about the effect of ions on hydration, and then you go to photo response of primarily bismuth vanadate, and then in the final part I'll tell you a bit about this olivine dissolution and the first steps that we have made in that direction. Okay, by the way, I mean, interrupt me at any time if you like, right? And we should keep it interactive. Okay, so the key approach that we're using is that we bring two solid surfaces in close proximity, where one of them is attached to an AFM cantilever, and then we measure the forces and extract, basically deduce whatever interaction arises from there. And then, of course, as well, now probably all of you are aware of, if you put a solid surface into water, because of the high dielectric constant of water, the interface very easily can acquire some charge by various mechanisms, being deprotonation, be it by deprotonation of surface groups or by adsorption of ions. And then what arises is a screening layer. If we're talking purely about the electrical part, then it's the electric double layer that extends some nanometers into the fluid. And of course, if you have a single surface that assumes an equilibrium configuration, if you bring two such clouds together, then you're no longer in equilibrium, and then there will be a gradient in energy, and that will give rise to a force, which you can detect with your AFM, and then you can try to decompose these forces into various components. And what we're going to do is exactly follow that scheme, very traditional colloid science, that we describe it as a contribution that will either be a van der Waals interaction or an electrostatic Poisson-Boltzmann derived force of disjoining pressure here, the pi, and on top of that, there's all other non-DLVO forces which then arise from, for instance, hydration or other parts that are not included in here. Of course, all this is very nice and works fantastically out here in the diffuse part of the electric double layer. Everything becomes difficult. What happens inside at the interface, right, where the surface chemistry takes place, and where we don't have such simple universal physics models that allow us to calculate the forces. What I find important is that to stress is that, of course, these forces that we sense with the AFM tip are, to the extent that we're characterizing the bare solid-liquid interface, are also the forces that are experienced by any reactants that need to go to a surface to pick up an electron or get rid of one in order to form some reaction. So all this is in principle well known. So what are the specific things that we have been developing in our group? That comes on the next slide. Before that, I should have pointed still to the idea that very often when we're talking about the electrostatic forces, and what we're going to do a lot throughout the talk, is we're going to be interested in the surface charge. And if you look at the expression for the double layer for the electrostatic disjoining pressure, you see that there isn't really directly a surface charge. It merely appears as a boundary condition when you're solving the Poisson-Boltzmann equation. And so that's what we're going to have to derive or determine by self-consistently by solving the Poisson-Boltzmann equation to fit our force curves. Okay, so what did we do? We basically developed this approach where we do with two different types of tips, measure two different things about the surfaces. The one being determining the surface charge on the surface, and the other one the atomic structure. And so the key difference is essentially that in order to resolve anything like an atomic molecular structure, we need to have very sharp tips, obviously, where we use the sharpest that we can get. This is a TEM picture of one after a series of measurements. So, and you see sort of a mica lattice here at the bottom to scale. And then well, you can see the lattices, and in lucky cases, you can also convince yourself that you see things like absorbing ions, or you can describe a hydration structure. If you want to learn something about electrostatics from these tips, that's usually not possible because, well, typically these are everything that I'm going to show you are silicon tips with an oxide layer on top. And if you immerse silicon oxide into water at room temperature, the surface charge density is actually pretty low. So if you have a tip that has sort of 1-2 nanometers in radius, the chance that you have a charge there is just a few percent. So in order to sense electrostatic forces, we need a somewhat blunter tip. And so, well, we have various ways of how we either intentionally blunten these tips or start with blunter ones, typically with a radius between 10 and 20 nanometers. In lucky cases, perhaps also a little bit below 10. We can also sense the electrostatic forces. And then basically we do in dynamic mode force distance spectroscopy. And then when you measure sort of a silica tip against a silica substrate, as it's shown here, then of course, as you approach the surface, you get in red a repulsive force. And then for this specific example here, where we have a gibbsite particle absorbed to our surface, well, we see as we're on the surface, we see the blue attractive forces from which we then can qualitatively already infer that the surface is probably positively charged. So if we take the same data that were shown distributed here and plot them in a line graph, you see two different things. Well, first of all, the curves on the silica substrate, they are very nice and homogeneous. They all collapse into a single band. On the gibbsite particle, well, there is a somewhat wider spread if you look at the center. And then there are some curves that are sort of taken at the edge of the particle, where with AFM you always have a little bit of doubts whether you don't have topography artifacts. So we'll disregard these green ones for the time being, and consider this here as the characteristic gibbsite response, and this as a characteristic response on silica. What you then also see is those black lines, and those are solutions of the Poisson-Boltzmann equation, either for a constant charge boundary condition, CC, or constant potential boundary condition, which basically means that as you assume that as you bring tip and sample close together, either the potential or the charge remains constant, and what you see that neither one is true, and reality lies somewhere in between. And to repair that, the reason for that is that obviously as you bring your tip close to the surface, well, the tip brings along with it its own cloud of counter ions, as the surface also has one. And then when you start to overlap those two clouds of counter ions, obviously the local composition of the electrolyte changes. And then if the charge at the surface is generated by some surface speciation reactions, protonation, deprotonation, or cation adsorption, then as you're changing the local concentration, you're shifting these equilibria back and forth. And that is basically the essence of charge regulation, and why the measured curves typically lie in between those two cases. And indeed, if we put the charge regulation solution, it lies perfectly in between here, or it fits the data, and the fit parameters that we get out of this are then the pK values for the speciation reactions that we have put in. I'm not going to go too much into detail. If you have more questions, I'm happy to explain that in more detail. What we then did basically is we studied exactly this system, sort of the same particle, if you wish, well, a few series for a series of salts and salt concentrations that are typically abundant salts in seawater, and then we extract what we extract is the charge density that amounts. So that is the extrapolated charge density for infinite separation of the two surfaces. And I'm writing here minus diffuse layer charge density. So that means, okay, so this is the charge density that arises from everything that is strictly at the surface plus whatever happens in the stern layer. Because essentially the force that we experience is the osmotic pressure from the counter ions in the diffuse layer, and that is what generates our force, and minus of it is then that's what's left on the surface. So what you see on this graph basically is, well, let's first look at the silica. You increase the salt concentration, you get a larger negative surface charge density. That is basically because if you improve the screening, it's more easy for the system to charge, and that's energetically less costly. So that is true for the monovalent sodium and potassium chloride here. But you already see when you do calcium or magnesium, the increase is basically absent. So this is presumably due to an absorption of calcium and magnesium ions to the silica surface. What's most interesting, what I'd like to discuss in some more detail, is this peculiar behavior of the gibbsite surface for the divalent cations. So monovalent essentially, okay, it's positive and it increases. You could say, yeah, largely that's probably also just improved screening. But for the magnesium and the calcium, see this distinct first increase in the calcium in the already positive charge density, and then followed by a decrease. How come? As we add more of the salt, well, okay, good. I mean, what can drive the concentration up? Well, you would in the first place assume probably you're absorbing calcium, and then maybe later chloride. Is that what brings it down? So this is something that we've been worrying quite a bit and wanted to understand in more detail. before looking into this, what I'd like to also to point to you is the typical number here, right? I mean, this is sort of 0.1 electron per square nanometer is the typical surface charge density and this is sort of the number that you extract also when you convert zeta potential measurements into charge densities. And what I find really amazing about this is sort of this is an almost universal value. I mean, when you do a titration with zeta potential, well, if you measure 5 millivolts, it's very small. If you measure 100, it's huge. So the dynamic range of these electrokinetic measurements and also the dynamic range that you get in the diffuse layer is enormously small. While at times you may have substrates that are intrinsically totally uncharged and others that carry a very high intrinsic charge density in the lattice. So this tells you that what you measure in a diffuse layer is heavily screened and almost universally for whatever material we've ever looked at. So we tried to get a little bit more in detail, and then we took this Gibbsite example, and then we tried to do now with sharp tips high resolution imaging, and of course, if I have seen the ultra high vacuum high resolution images, I'm almost about to remove this. Okay, it says atomic resolution. It's not high. Okay. Anyway, you see an atomic lattice, and it matches with what you expect based on bulk crystallography. It's not more than that. And if you do that in pure water, or if you're throwing in sodium or potassium chloride, it always looks the same. We don't. Well, okay. Some optimistic people might at times attribute a bump that you see to perhaps an ion that sticks. Maybe that's true, but it's not something that is very tangible. But when we throw in the divalent cations, magnesium or calcium chloride, then you clearly see a change in symmetry. Huh? I mean, here you all of a sudden you have sort of zigzag double rows that appear, and at an intermediate concentration. And if we go to higher concentration, where sort of the charge density kicking back down again, then you see a second process where every other of these double rows becomes a bit brighter and the one in between a bit fainter. So we were you might be optimistic that, oh great, these are then the calcium ions that absorb, and then the chloride ions on top. So that was sort of our first thought. But then there does come, of course, a problem, because now we have numbers, and if we sort of the size of the lattice, and if this is all a calcium ion, then we end up having 4 unit charges per surface unit cell. That's about 100 times the charge density that I was just telling you about, right? So now, how comes that we have teamed up with Martin Anderson from Susan Stipp's group in Copenhagen at the time, and they did for us some DFT calculations. Now, this was an effective medium DFT with many limitations, obviously, but nevertheless, I think it was a very remarkable result. So in the first place, they did regenerate, they recovered this zigzag double row structure that we had seen in the experiments. That was very good. And then they also found that the structure is most stable if the calcium ions remain hydrated. And then each calcium ion would share 3 hydration waters with the Gibbsite surface, which would deprotonate. And so that, and then in addition, they also found that there is the zigzag is slightly asymmetric in the simulations. We have some experiments that look like it, but others not. So that's perhaps not very clear. But anyway, in the simulation, it turns out to be asymmetric, and there seems to be another water molecule that deprotonates that becomes an OH minus in a bridge site. So that's actually cool, because now we have 2 calcium ions and we have 4 OH minuses per unit cell, and that's essentially what we need. Essentially, that surface is neutral, and our 0.1 electron per square nanometer, that's only 1 in a few tens of unit cells that actually carries charge. So if you look at that number. And then basically what happened when they increased the salt concentration, then a chloride ion from the bulk came and kicked out this OH minus in the bridge side. Oh no, I did not tell, sorry, I did not tell you. So where does then the positive charge come from? The positive charge that we see here, why does it go up? That came because this OH minus here in the bridge side can protonate from the solution. And so the mechanism that generates this increase is that, well, in the first place, the two calciums and the 4 OH minuses compensate everything. Then a few of the OH minuses here get protonated. That generates the positive charge density that we see. And then as we increase the salt concentration, this bridging water is replaced by a chloride. But of course, the chloride never gets protonated. And thereby the mechanism that generates the positive charge disappears. And that brings the charge density back down. Now, okay, the details of this mechanism may or may not be 100% true. But what I think is very clear, it's an enormous amount of charge compensation that happens within that Stern layer, and water ions play an essential role. And this is something that I think is needed in order to explain this general observation that whenever you do an electrokinetic or colloidal scale surface charge measurement, you basically always see this 0.1 electron per square nanometer roughly. All the differences between different materials, they are largely compensated away by be it ions or just protons or OH minuses in a Stern layer. And for sure, if you see this kind of complexity that is in this picture, it also becomes somewhat questionable, or perhaps to use these simple surface speciation models, or in other words, something that we have also seen very often, these surface speciation models, they always describe your data, but when you want them to be predictive for a new condition that you're exploring, their power is very limited. And this is, I think, because these simple, here is a cation that complexes with an OH group on the surface, it just usually does not do justice to the actual complexity of the processes that take place. So that was sort of the lessons that we have learned from these experiments on the gibbsite silica. Okay, so this basically finishes part one, and now we have this tool that allows us to measure surface charge density. And now let's look at how we can characterize heterogeneous surfaces. And so continue first with our gibbsite, our favorite gibbsite. And now here we have converted all these forces into surface charge densities. And you see, if we do that at pH 6, well, we get the homogeneous repulsion on the silica, and we get the more or less homogeneous attraction on the gibbsite. But if we increase now the pH, you start, you start to see that essentially you start to see some structure inside this gibbsite nanoparticle. And well, some of these, if you look at the same time here at the topography image, you see that these lines here correlate with some of the visible defects that you have on the surface. And that's, of course, not surprising, right? These steps, there's lots of broken bonds, molecule atoms with different coordinations. And of course, they are prone to respond differently to changes in the composition of your fluid. So we can indeed get a hint of the reactive locations on the surface, albeit with a lateral resolution of perhaps 5 nanometer or so, which is what we need in order to sense these electrostatic forces. What you also see is, well, okay, you also, I mean, in the beginning I said I'm careful about whether it's a topography artifact at the edge of the particle. Now here I'm only changing, it's the same particle and the same tip. So if something changes really dramatically, it's probably not a topography artifact. And in fact, we think that this wide rim here correlates actually with a strongly increasing density of steps as we approach the top edge, basically, of our particle here. Now, this was still a relatively simple platelet-like particle. Then from there on, let's move on to something more fancy. So these are strontium titanate particles. They have these truncated dodecahedron structure, if I'm saying that properly, which I always hesitate, but I think it's true. So you see squared 100 facets, and you see hexagonal 110 facets, and you see them both in the STM and in the AFM. And so now we take these samples, we fix them on a substrate, and we dump them into water, and look at what we see, and then indeed what you see on this image here, it's a force gradient map. Essentially, it shows you that the hexagonal facets, they tend to light up in a yellow greenish color, which is here on the side of a repulsive force, whereas the square 100 facets, they all light up in blue, which corresponds to an attractive force. And indeed, if we average over these areas and we do our DLBO fits, we can extract surface charge densities which are negative on the 110 facet and positive on the 010 facet. So now that basically means now we have a single nanoparticle, and within a distance of a few tens of nanometers, we can measure these different surface charge densities. And of course, if we can do that at 1 pH, we can also do that at multiple pHs. So then we see here, okay, you go to low pH, you get attractive forces, positive charge densities all over the particle. You go to very high pHs, you get repulsive forces and negative charge densities all over the particle. But in between, you have this window of pHs from about 4 to 6, where the 110 facet has already switched sign, whereas the 100 facet is still positive when you come from low pH. So what we have now basically from all this is sort of titration curves that we have measured now on a single particle. And we see that within these couple of tens of nanometers distance, we get different reversal of the surface charge density. About sort of approximately 2 pH units, the surface separated from each other. So what you also see is here is this is the potential of zero charge that we've measured from electrokinetic mobility, and it's surprisingly, perhaps at first glance, it lies outside. It's not on the average curve. So this dashed line is sort of the area weighted average of the two others, and it lies below. And I'll come back to that in a minute. But now what's very important, of course, in the first place, there is nothing like a potential of zero charge for the entire particle. There is a potential of zero electrokinetic mobility, but that doesn't mean that the individual parts of the particle don't carry any charge. What you can do now, basically, you can say, okay, if I'm in this intermediate range, it should be interesting because I have the two facets have opposite charge density. And indeed, we explored that to look at colloidal heteroaggregation. So we were throwing in some very small 20 nanometer Ludox particles, silica particles into the solution. And if you do that at low pH, so those particles are negatively charged. If you do that at low pH, they decorate the full particle. At very high pH, they go nowhere. At an intermediate place pHs, you can selectively decorate the 100 facets as you would hope. And indeed, we've tried this now also with gold nanoparticles. So this allows you to do sort of a facet selective deposition of co-catalyst particles. That's sort of the idea that arises from here. Now, why is this thing here outside the window where you would expect it to do to be? To do this, we went back to high resolution imaging of these particles, and then you see, well, in the first place, you do see again the facets, and you zoom in, you get a lattice resolution on both types of facets. There are rather few defects. The pattern of bumps that we see is consistent with bulk termination of those of the crystal. Well, what we also see though is that at the transition, at the edges between two adjacent facets, you have quite some disordered regions, and in particular here at this corner, there is a wide region where there is no atomic lattice to be resolved, and you have lots of broken bonds. And this part is also turns out to be negatively charged, and in total it makes up something like 20 or 30% of the total surface area. And this is why we believe that the zero electrokinetic mobility lies at an even lower pH than the area average value of those two facets, because of this negative charge. Yeah, what you also see, well, of course, what we don't really know is what is the termination of those two facets. I wrote down here something which we sort of infer from the belief that strontium tends to leach relatively easily into the solution. So we don't think that we have a strontium, that we can have any strontium at the surface. And then that one could also be, of course, involve some titanium. But then here it would be consistent with the negative surface charge density that we see on the on those 110 facets. So if we nevertheless like to describe this with some surface speciation reactions, well, then you can again, that's what generates these fit curves that I showed you. But of course, this should be taken with an enormous grain of salt in view of all the microscopic processes that are probably underlying it. What we find interesting in addition, well, okay, good, it does again, nominally, this is a super highly negatively charged surface, but again, the number of the density is still very low, so that reiterates my point that I made before. But to go beyond that, what we were also interested in is the hydration forces, and there we also see a strong difference between the two facets, so being much more pronounced on the 100 facets than on the 110. And the reason we believe is that in the 110 facet, in one direction, the distance between two adjacent adsorption sites for water molecules is particularly large, and it's actually too large to do an efficient intra-layer hydrogen bonding. And so what we believe is that this basically frustrates the hydrogen bonding network and gives rise to a less stable hydration structure on the 110 facet in this specific case. So it would be nice if someone would do a very good DFT simulation to prove that, whether that is really true. But that's sort of what the picture that we have. And of course, if you think that that is true, then of course you come back to catalysis and think, hey, then every water molecule, every reactant would see a very different hydration shell to jump across when it wants to do a reaction with strontium titanate. True. Yeah, true. I mean, okay, we do not do any 3D mapping. It's also on these colloidal particles. Not so easy as on a flat surface. That is in principle true, but of course, I mean, this is a consistent picture from many measurements. So we're pretty confident that these differences, even if they arise perhaps from some microscopic things that we don't resolve, they are characteristic for the differences between the 100 and the 110 facet. Could be that if you have really a good position resolved for spectroscopy within your unit cell, you probably go beyond it and provide more detail that we don't have. So these are sort of all these different curves that you see here are sort of averaged as the tip, well, drifts around while you're doing the measurements in the XY direction. So it will be hovering maybe, I don't know, 1 by 1, 2 by 2 nanometers or so while you're doing these 100 curves approximately. Yeah, okay, but nevertheless, we do find that very exciting. You see very systematic differences. And of course, well, many of you know better than I do how much of discussion there is in the catalysis community that the hydration structure really matters for the reactivity. Well, this is now a platinum 111, so a hydrogen evolution that's totally different from strontium titanate. But the key point still is that that these well, frustrations in the hydrogen bonding network can have a very big effect. And well, indeed, I mean, the interpretation that we're using is based on that solvent tip approximation, which in a number of MD simulations with all atoms, including the tip, different clusters, has been reasonably well proven that basically it's the hydration structures of the tip that interact with the hydration structure of the substrate. And so to a good, well, to a reasonable good approximation, at least you can interpret those forces then essentially as a potential of mean force that represents the density distribution of the water molecules at the interface. Of course, there are limitations to that, but it's been found to work reasonably well in many systems. So basically, from the measured force profile, you can infer back to a density profile at the bare surface. And so this is something that we have been trying quite a bit, also to interpret force distance curves on mica that we did systematically with a variety of different alkali chloride salts some years ago. And it was a pleasure to hear this morning and discuss also with Alper extensively and Florian that indeed many of the simulations that you have been doing here indeed reproduce key trends of what we have seen at the time. And so the key observation at the time is shown here. Again, this is not position resolved. This is averaged, and our tip has probably probed a few unit cells as we were doing these measurements. But what we do see when we average, okay, so this is pure water. You see a nice and pronounced hydration oscillation, reasonably symmetric around 0. If you do that for lithium chloride solutions, well, the oscillations are superimposed onto an overall repulsive background that becomes less repulsive for sodium chloride, is kind of neutral for potassium chloride, and turns into an attractive force for the larger rubidium and cesium cations, where in particular for those two, we see the oscillations of the forces essentially disappear. So there's our, so overall we see the hydration force consists of, well, these two contributions, an oscillatory one and a monotonically decaying background, and that the latter one changes sign with increasing salt cation size, and the hydration, the oscillatory part disappears for the larger ones. And the interpretation that we have proposed is that it is related to the poorer hydration, much weaker hydration of the larger alkali cations that then basically disrupts the water structure. And in those days, together with Nadine Schwiertz, we did MD simulations of our system, and indeed they found that the density, the water density here in dark red, is a lot more pronounced oscillatory. The oscillations are a lot more pronounced on the lithium, become less pronounced potassium, and then they are, well, they're the first oscillation still, but then pretty much suppressed in the case of cesium. And then indeed we used this solvent tip approximation to basically get from the Boltzmann factor, calculate the forces based on the measured density profile from the simulation. And indeed that produces a force profile that well, in any case reproduces the disappearance the strong oscillations that we also see in the experiments. So we believe that that's really what we are seeing. And well, as I said, I was glad to see this morning that indeed this is also what's found now here in much more detailed analysis of these MD simulations. So what we found, so let me come back here. There is nothing about this background force. So let me go back to that monotonic background. We have, so what we find very effective is that there is an old idea from Mugele and Radic from the 1970s even, who argued that they proposed a mean field model where they say basically, okay, you have water that is somehow anchored to a substrate, and that gives a and so there's a sort of polarization field. And that polarization field, as you move away from a certain surface, obviously decays until you get the isotropic bulk about a nanometer or so away from the surface. And now if you bring two surfaces together and they have the same type of anchoring, that means that like a silica tip and a mica surface without cations here, then those two dipole fields oppose each other, and that would then give rise to a repulsive force. But on the other hand, if you are able to flip the average orientation of the water molecules, for instance, by absorbing a cation that has a very strong polarization or anchoring of the water molecules, then you can have a situation where they're oppositely arranged, and you get an attractive force. So what we tend to think or ask basically is it true that this flip in the background force that we see in the experiments is indeed caused by this different hydration forces and the anchoring? And we did see this in a very similar way also if we then went, well, okay, so first it was cesium, now we're going to calcium, which has even stronger effect. And indeed, for calcium and magnesium, we both see this flip where the background force on top of the oscillations becomes strongly attractive. And we see that very pronouncedly on mica, but they're not less or not at all on silica, where the calcium absorbs much less than it does on mica. So we tend to think that there could be a sort of an attractive hydrophilic hydration force that emerges from such asymmetric anchoring. But that's certainly something that would be great to see in SFG, but I think you cannot confirm that. Okay, that's sort of one of the things that we feel very much excited about, and that we would love to study in more detail. I'm looking at the time and I get scared, right? So do you as well? Okay, that's bad. So then let me at least okay, good. Let me then immediately jump to the photocatalysis part and at least show you those things. Then I'm going to skip the explanation of what photocatalysis is for you. But of course, it's important that you separate the electron hole pairs in your photocatalytic nanoparticle, and for that people have came up with this idea. Fantastic, when you use these faceted particles. And of course, different facets have different work functions, so that generates an internal electric field that separates the electron hole pairs. And that's what has been also compared to DFT calculations in vacuum. But of course, being colloid scientists and having talked about all these solid-liquid interfaces, know that all this is going to change a lot when we want to really split water, and then we have to throw the thing into water, into solution. And that is going to affect all these surface potentials. And what are the consequences of that for reactivity? Well, here is an example where we did photodeposition on bismuth oxybromide many years ago with Guido Möl's group. And there we saw for the first time that we could, merely by changing the pH of the solution, we could change the pattern in which we could deposit, reduce basically gold and deposit gold particles on these facets. And similarly, lead oxide was also, we could clearly steer the position on these particles where we would get the photodeposition. And then we wanted to do this directly, basically, on our strontium titanate particles. Unfortunately, that of course has a very high band gap, and for technical reasons, we didn't get that into our AFM. So we had to switch to bismuth vanadate, which, okay, is nice because it's also perhaps more relevant as a visible band gap semiconductor, but it's a pain to work with when you have worked with strontium titanate. It's a lot less stable, but okay, bottom line, you see things going up and down. So there is indeed a reversible change in the surface potential, and we can do the same kind of force analysis that I just showed you before. And indeed, again, we have two titration curves that are somewhat shifted with respect to each other. And in both cases, there is a response to illumination. What we do see that in both cases, in both facets basically tend to get more positive as we illuminate the surface. So you presumably that would have to imply that the particle itself changes its charge, its total charge in the solution upon illumination. Qualitatively, that you get that we get an accumulation of holes at the surface is expected because it's an N-type semiconductor. So you would expect the holes to go to the surface. What is important is, again, what we have seen, the photo response that we see in our diffuse layer potential is a lot stronger than what this is from Canli's group has reported on bare bismuth vanadate particles in vacuum or in air. I don't remember exactly in the past. So there's a very clear effect. And it depends on pH, and it goes a bit all over the place. So this is a bit scary. Also, I mean, we've been suffering really a lot, the poor student, about the reproducibility of these particles. They're a lot less nice from the synthesis than the strontium titanate. There are defects, there are little microfacets and steps all over the place, and we could never really avoid them. You see also when you do get every once in a while a good lattice resolution, you also see all over the place many defects, and even things as simple as sort of a unit cell step turns out they can have an enormous effect in the photo response. So this part up here, this is just in the topography, this is just a unit cell step, and you see that from dark to illumination, you see a dramatic effect of these defects on the photo response. And then we basically, in essence, we just have very poor statistics, which makes it very tough to draw very hard conclusions. Beyond that, defects are really relevant. Okay, well, given the time is up, then I will basically not show you the things that essentially say everything is very complicated and we have not come to very good conclusions yet. So then I'll, well, thank my group. I'd like to single out Igor Sirietanu, who is our AFM head and coordinator and has been for a long time. Sue did all the measurements on the strontium titanate and bismuth vanadate. Simone did the measurements on the mica hydration forces with the different ions. Thank you very much for your attention.